Okay, cool. All right, so this is a section, I've not taught this a ton. You guys got a little bit of exposure to it last year when we did vector addition. And that's basically what this boils down to, okay, is it's going to just be vector addition with some slightly new terminology and a couple new concepts, okay? I was looking through these notes a little bit during tutorial, and I think I might deviate a little bit from the notes here. So anyway, let's see what we got. So, yeah, I remember reading through all this. I need to rewrite this. I'm not super happy with this. So this is the stupid book explanation of what relative motion is. I think I'm going to give you a different explanation. All right. All right, so let me do this. All right, here's a person. He's standing, okay? So right now his velocity is 0, okay? Now, usually, 99% of the time, when we talk about an object's velocity, we're talking about its velocity relative to the Earth, right? Okay? So this right here, when I say that this is the velocity of the person, we're going to use the following notation. We're going to write that this is the velocity of the person relative to the ground. Okay? Now, here's that same person. Here's that same person, but now they're in a bus. Okay? So the person is just standing there. Okay? So that means that the velocity of the person relative to the bus is 0, right? Because inside the bus, they're not moving. They're just standing there, right? Follow? But if the bus is moving, then the person's moving. Sort of. The person's moving, but not relative to the bus. The person's moving relative to the ground. Follow? All right? So, if the velocity of the bus relative to the ground is, I don't know, I'm going to make up a number, say 15 meters a second. Well, then that means that the velocity of the person relative to the ground is 15 meters a second, right? Right. Okay? So, it turns out that here's the notation we're going to use. So if I want to find the velocity of the person relative to the ground, it's simply just vector addition. All right? And here's the equation that you do. So to find the velocity of the person relative to the ground, you're going to take the velocity of the person relative to the bus plus the velocity of the bus relative to the ground. All right, and this is sort of it's sloppy, but if it helps you memorize the process, the two things that sort of cancel are always going to be sort of next to each other. Do you know what I mean? Like the b's are in the middle. So when you add these two vectors, those b's kind of cancel out, and you're left with the velocity of the person relative to the ground. Good? Okay, so let's do this. Here's our person. So the velocity of our person relative to the bus is, I don't know, let's say 5 meters a second. Okay? But the bus is going this way relative to the ground at, let's say, 20 meters a second. So the idea is the bus is driving this way at 20 meters a second, but the person's running towards the other end of the bus. So the two velocities are kind of working against each other, right? Does this make sense? Okay. So if we wanted to find the velocity of the person relative to the ground, what's up, Cam? Exactly, I was going to get there, yeah. So yeah, so Cam just said the 20 meters a second should be negative. Do you guys see why? Pointing in a negative direction, right? Good? So yes, exactly. All right. So this means that the velocity of the person relative to the ground is the same as the velocity of the person relative to the bus plus the velocity of the bus relative to the ground. So that's going to give us, let's see, they're running to the right at 5 meters a second, but they're in a thing that is moving backwards at 20 meters a second. And so their overall velocity is negative 15 meters a second. So that's the velocity of the person relative to the ground. Oh, I'm sorry. Remember that time I broke your ankle? All right. Does this make sense, you guys? All right. Now, very often you need to subtract or you need to rearrange these things. All right. So a couple other things to be aware of. So in this example, the velocity of the bus relative to the ground is negative 20 meters a second, right? So like if you were standing on the ground watching the bus, you would see the bus going this way at 20 meters a second, right? Follow? Now, what about this then? What's the velocity of the ground relative to the bus? If you're in the bus watching the ground go by, what's the ground doing? It's just standing there, sorry. Isn't it going the other way? Right, here, look. So when you're in your car watching the telephone poles go by on the freeway, they're going backwards, right? In the opposite direction the car is going, right? So you can always, if you know the velocity of, in this case, the bus relative to the ground, then the velocity of the ground relative to the bus is just the opposite. That is a very useful trick, and we're going to use that in an example here in a minute. Follow? Questions? Okay, so this is relative motion. Now, 99% of the problems we solve, all of our velocities and things are written relative to the ground. Okay? But there are times when you can't do it that way. Okay? So last year, you may remember, we did a problem where there was a conveyor belt going this way and an ant was crossing the conveyor belt, right? Okay, so if you wanted to find the velocity of the ant relative to the ground, you had to take the velocity of the conveyor belt relative to the ground plus the velocity of the ant relative to the conveyor belt and add those vectors up, right? Okay. So the one thing to be aware of is, in this example, it's one-dimensional, right? How would we deal with it if the bus was going this way, but you walked this way? You got to do vector addition, right? Follow or no? Okay, so I will do an example like that in a minute, but that's the deal. All right, so any questions about kind of what I've gone through here? All right, so let's run through an actual example. This example illustrates something that is super, super, mega crazy important in the world of physics. All right? So it is very important that you follow along with this. All right? Good? Questions before I go on? Is everybody okay with the notation? Okay, so if I write V, A, B, that means the velocity of object A relative to object B. Good? All right. So in this problem, there are two objects. There's a school bus and a motorcycle. Okay? So here we go. Let's start by writing down what we know. So first of all, I'm going to use B for bus, and I'm going to use M for motorcycle. Good? All right, so let's write down what we know. So it says you're in a school bus that's traveling east at 25 meters a second relative to the ground. So the velocity of the bus relative to the ground, I'm going to put an I next to this for initial because it's going to change in a little bit. Okay? So the velocity of the bus relative to the ground initially is positive. I'm going to put a plus on it just to emphasize the fact that I checked the sign. That's 25 meters a second. All right? Now, it says a small motorcycle travels away from you, travels away from you at 35 meters a second, again relative to the ground. Okay? So the velocity of the motorcycle relative to the ground is 35 meters a second. But since it's going away from me, I need to make it negative, right? So let's put some arrows on this. This guy's going, oh, fart.
That kind of doesn't work, though. Because, like, you could be leaving it too, right?
Away from you, like going backwards.
Yeah, it's worded awkwardly. It means going the other way. It's worded awkwardly. All right, I'm unhappy with my drawing, though, so I'm going to do a thing that's going to piss you all off because you can't do it, and I apologize. Sorry. I'll give you a second to update your notes. I'm sorry. Oh, hey, Josh. How's everything?
All right.
Good. Because I switched the two positions. I made it so that they were moving apart from each other. Before I had them moving towards each other. Follow?
Yeah.
All right. Sorry. I'll wait till everybody is done updating. Is it hot in here? I'm dying all of a sudden.
I'm freezing.
Really?
I am not. That's a good
Yes, you are not.
All right. Well, you guys are just going to deal with it.
Definitely not. That's right.
Okay. All right. So question number 1 says, what's the velocity of the motorcycle relative to the bus? Everybody good with what's up here so far? Everybody got their notes corrected after I flip-flopped everything? All right. So the question wants to know, what is the velocity of the motorcycle relative to the bus initially? So based on what I just taught you, well, let's see. The velocity of the motorcycle relative to the bus initially ought to equal, let's see. It's the velocity of the motorcycle relative to the ground initially plus what? The velocity of the ground relative to the bus initially, right? Right? Because then the two G's cancel and you're left with motorcycle and bus, right? Follow? All right? But the problem is, so I know the velocity of the motorcycle relative to the ground, but I don't know the velocity of the ground relative to the bus. Or do I? What are you saying back there, Teddy? Yeah, remember, if this is the velocity of the bus relative to the ground, then you just flip-flop it, right? So this is the same as bless you. Oh, that's not what I wanted to do. I was trying to do a big in it instead of in small in it. There we go. There we go. All right, so does everybody understand how I got from here to here? Because it's technically plus negative, right? Because remember how I showed you guys that to switch the order of the two things, you just add a negative sign? Like here, we went from the velocity of the bus relative to the ground was negative 20, so the velocity of the ground relative to the bus was positive 20.
Are you minusing out negative?
No. It's plus. The negative means opposite. All right, so is everybody good up to here? All right, so let's plug in our numbers. Let's see. The velocity of the motorcycle relative to the ground is negative 35 meters a second plus negative, let's see, the velocity of the bus relative to the ground is 25. And so we get negative 60 meters per second. Yes?
That's what the other one I found, like VDM first. Can you just like switch that after that?
Yeah, that's fine. Yeah, I got
It doesn't
you.
really matter.
Yeah. I think you're making it a little harder because you got to do 2 flips then.
I only did one. I flipped GM to MG. No, MG to GM.
You flipped mg to gm.
Positive 35 plus.
Then that would give you the velocity of the bus relative to the motorcycle.
Yes.
That gives you positive 60, so then you got to flip it again
Yeah, yeah.
to
No,
get negative
that was
60.
the answer to number 2. I just.
Oh, I gotcha. Okay, are we good with what I did here? Yes.
So when you have like acceleration or not acceleration, you have
Velocity.
velocity, and it's like relative to 2 things, like they're relative to each other. Does the negative just indicate they're going away from each other and positives towards each other?
No, not necessarily, because you could have 2 things going in a negative direction.
Oh, okay. So
Follow?
you just so you just have to look at the you just have to know.
Yeah. Good?
Yeah.
All right, so what does this mean? So what this means is if you're, so this is the velocity of the motorcycle relative to the bus. So it means if you're standing inside the bus, watching the motorcycle, to you, the motorcycle is going to get 60 meters away from you every second, and relative to you, it's moving west. Follow? So I wrote myself a little note about the spool thing here. It says, remember to me, spool explanation. The idea is the 2 things are moving apart from each other, right?
Yeah.
This one's going this way at 25, this one's going that way at 35. So every second, they're getting another 60 meters farther apart, right? So if you had a spool of rope that one end was tied to the bus, and the other end was tied to the to the motorcycle, as it drove, it would be pulling out 60 meters of rope every second. Follow or no? All right, so that is question number 1. Is everybody good with question number 1?
Yeah.
All right, so I see now what you were saying, Daniel. That is totally fine. All right, question number 2 says, what's the velocity of the bus relative to the motorcycle? You just flip it, right? So let's go back and kind of clarify this. So this is all number 1. So this is the velocity of the motorcycle relative to the bus initially. So question number 2 wants to know what's the velocity of the bus relative to the motorcycle initially. Well, that's going to be positive 60, right? It's negative velocity of the motorcycle relative to the bus initially. So it's negative 60, which is positive 60. Are there questions? All right, this is all going somewhere. So, would it be horrible if I erased this stuff?
No.
Okay, so. All right, so I'm going to kind of summarize real quick. So here's the stuff that we know. So we know that, let's see, the velocity of the bus relative to the ground initially was positive 25 meters a second, and the velocity of the bus relative to the motorcycle initially was, what did we just get, 60? Yes. And we know that the velocity of the motorcycle relative to the ground initially is negative 35 meters a second, and the velocity of the motorcycle relative to the bus initially was negative 60 meters a second. All right, so that's what we've just figured out. Everybody good up to there? All right, problem number 3 says, suppose the motorcyclist slows down and stops his motorcycle relative to the ground in 10 seconds. What is the motorcycle's acceleration relative to the ground? Okay, so let's see. Here's what we know. Relative to the ground, I know that the velocity of the motorcycle relative to the ground initially is negative 35 meters a second, right? And then he's going to stop. So that means that the velocity of the motorcycle relative to the ground final is 0. And I know that this all takes a time of
30 seconds. Or 10 seconds.
yeah, 10 seconds. Follow?
Yeah.
So, we ought to be able to find the acceleration now, right?
Yeah.
Relative to the ground, right? So, our acceleration of the motorcycle relative to the ground is velocity final minus velocity initial over time. I'm being a little sloppy with my notation. This should all have mg. I guess I should actually do it. This is not the time to skimp. final minus velocity of motorcycle relative to the ground initial. All right. Tedious. Bear with me. This is going somewhere. So, is everybody okay so far?
Yep.
Yeah.
All right. So, velocity of the motorcycle relative to the ground final is 0 minus velocity of the motorcycle relative to the ground initially is negative 35 divided by 10 seconds. That's going to give us 3.5 meters per second squared. Notice positive, right? Because the motorcycle was going in a negative direction, and then that velocity got less negative, so the acceleration is positive. Questions on this? Everybody good? All right, number 4. Now we're going to find the acceleration relative to the bus. Now we're going to find the acceleration of the motorcycle relative to the bus. May I erase what I did in blue here? Shh. All right, this is neat. So number 4, find the motorcycle's acceleration relative to the bus. So let's see, the velocity of the motorcycle relative to the bus initially was negative 60 meters a second. So to find the acceleration relative to the bus, what other thing do I need to know that's not written on the board yet?
Velocity of the motorcycle final relation to the bus.
Yeah, I need to know the final velocity relative to the bus, right?
Yeah.
So, do you see what I'm saying? Because we know that the velocity of the motorcycle relative to the ground final is 0, but we need the velocity of the motorcycle relative to the bus. Make sense? We don't know that yet. So we got to take a second and find it. So let's see. The velocity of the motorcycle relative to the bus final is equal to the velocity of the motorcycle relative to the ground final plus the velocity of the ground relative to the bus final. This is the same thing we did before, right? All right, so let's see. We don't know the velocity of the ground relative to the bus. So what should I do? This one's not written in my givens up here anywhere, so.
I just don't need it. Do something with it.
What's the bus doing, you guys?
Still moving.
Still moving. The bus hasn't sped up or slowed down, right?
Yeah.
Follow? So it's still 25, right? So this is the velocity of the motorcycle relative to the ground final minus the velocity of the bus relative to the ground final. Are we good or no? I know your eyes are glazing over. It's a lot of letters. Everybody follow what I've done or no?
Yeah.
Molly, you doing okay over there? Everybody happy? Sorry, you're just craning your neck is why I'm picking at you. All right, so let's see what we get. So velocity of the motorcycle relative to the ground final is 0 minus the velocity of the bus relative to the ground final is still 25, right? So there we go. There's the velocity of the motorcycle relative to the bus final. All right, something cool is about to happen, so if you've zoned out, zone back in. Are there any questions before I... Yeah, Sarah, what do you got?
Does this only work with velocity then?
Does what only work with velocity?
The whole, like,
Being able to add? No, that's sort of where we're headed. It works with position. Does it work with acceleration? It does work with acceleration also.
okay. So isn't there an easier way to do something?
That's sort of where we're headed. So yes, but I want to show you why. Yeah. Yeah, this is like a one-time, well, sort of a one-time thing. I know it sucks. It gets not as bad, which is why we're going through all of this now. All right? Are we good? Patrick, Peter, you guys good back there?
Yeah, we're talking trash about last week's trebuchets.
Oh, I gotcha. Fair enough. All right, is everybody happy?
Yeah, we're good.
All right, so, why is there no happy medium?
It could be a sad medium.
There That was good. I like that. Zoom. Okay, so, all right, I'm out of room. So here's the deal, you guys. Our acceleration of, what are we trying to find? The acceleration of the motorcycle relative to the bus, right? All right, so that ought to equal the the velocity of the motorcycle relative to the bus final minus the velocity of the motorcycle relative to the bus initial all over time, right? All right, I can't see them anymore because they're up there somewhere in limbo. What's the velocity of the motorcycle relative to the bus final? Negative 25 meters a second, right? Minus, what was the velocity of the motorcycle relative to the bus initial? Negative 60, agreed?
Yes.
All over, what's our time for this to all happen?
10 seconds.
10 seconds. What's negative 25 minus negative 60?
35.
35 meters a second all over 10 seconds. What do I get? 3.5 meters per second squared. Why are we saying whoa? What do you got?
Because since the bus's acceleration is constant, the same way that the ground's acceleration is constant,
I want you to tweak a word.
but they're zero.
They're zero.
They're both zero.
Good.
So, like, since the bus acceleration is zero, the same way that the ground's acceleration is zero, then the relative acceleration would be equal because they're both accelerating at the same rate of zero.
Yes. So here's the deal. There are what are called inertial and non-inertial frames of reference. All right? I'm not going to spend a ton of time on this. It's not on the test at all, but it's a thing that theoretically you ought to know about. Basically, so the textbook definition of an inertial frame of reference is an inertial frame of reference is one in which Newton's laws still apply. In other words, an object won't accelerate unless there's a force causing that acceleration. Okay?
Real world.
Yes. Now, suppose you're in a school bus and there's a tennis ball sitting on the floor. Okay? Relative to the bus, both you and the tennis ball are not moving, right? If the school bus stops, suddenly, relative to you, the school bus or the tennis ball is going to accelerate forward, right?
Yes.
With seemingly no force to produce that acceleration.
Oh. Okay.
Follow? You see what I'm saying? Like it went from not moving to suddenly, oh, now it's moving, and there was nothing pushing it, right? Okay, so that would be a non-inertial frame of reference. All right? So, here's the deal. It turns out, as long as your frame of reference is not accelerating, then it's called an inertial frame of reference, and so that means that Newton's laws apply. So, regardless of whether you're watching the motorcycle from the ground or the bus, since neither the ground nor the bus is accelerating, you have to get the same acceleration, and as a result, the same forces. Newton's laws still apply. You get the same answer whether you analyze it from the bus or from the ground. That's why you can drive down the road in a school bus. So you're driving down the road in a school bus that's going at 60 miles an hour. What happens if you throw a stuffed bear up in the air? This, right? Unless the bus speeds up or slows down, right? Follow?
Yep.
Okay? So, all of that is summarized in the notes here. Okay? So, here's what all of this garbage says, very briefly. Position, relative position. So the position of object P relative to A is the same as the position of P relative to B plus the position of B relative to A. So the same exact rule we just learned for velocity. Okay? So Joe is 5 meters from me. Sarah's 10 meters from Joe. Sarah's 15 meters from me. Okay? Now, taking the derivative of this gives you the velocity rule that I just taught you. Good? All right? And then, let's see. So if you take the derivative one more time, what ends up happening is you get that these are equal as long as the bus isn't accelerating, right? Like, when you take the derivative, one of these two things is going to turn out to be 0. Right? And so you get that the acceleration is the same either way. Yes?
Never mind. Sorry.
Did you raise your hand just so you could say never mind? That was what that seemed like.
No. I thought 2 of the things had to be constant in the velocity, but only one does, right? So you take the derivative of the constant.
Let's see. So in our example that we just did,
Both the bus and the ground had no acceleration.
correct.
But you only need one of those to not have an acceleration.
No, they both need to be not accelerating. So where does that come out here? Yeah, so here, the only thing that was accelerating was the motorcycle, right? So in this example, so here, object P is accelerating, okay? Neither A nor B are accelerating.
Okay. Okay.
Follow? And as a result, whether you measure the acceleration of P relative to A, which is not accelerating, or you measure the acceleration of P relative to B, which is not accelerating, you'll get the same thing.
Okay.
If either A or B are accelerating, then the one that's accelerating will give you an erroneous answer in terms of Newton's laws.
So 2 of the 3 objects need to have no acceleration.
Correct.
Okay.
Really good questions. I hope everybody just heard that. Are we good? Yes. All right. The reason this all worked, you guys, in that last example, we had 3 objects. Motorcycle, bus, and ground. In that example, the only thing that was accelerating was the motorcycle. Okay? Since neither the bus nor the ground was accelerating, if you find the acceleration of the motorcycle relative to the bus, which isn't accelerating, or if you find the acceleration of the motorcycle relative to the ground, which is not accelerating, you will get the same answer. If the bus was accelerating, then that would give us a different answer. Follow? Okay. Did that make sense? I think I did better with this year than I did last year. I still think I need to improve, but are we at least okay? All right. Now, all of these examples were one-dimensional. Two-dimensional is the exact same thing, except you need to think in terms of vector addition, which means components and stuff. But the process is the same. Okay? Like if you can get this idea written out, then draw your vectors and do your vector addition, it's literally the same thing we've been doing. Follow?
Yeah.
Okay, so let's see. Where did we get to? So we got through the motorcycle example. What time do we get out? 39? 45. Do we have time to do the elevator problem?
Not really. It's too long.
Oh, they are.
So it's an elevator.
I'm gonna temporarily hang on one second. Let me see.
Yeah.
Okay, I'm gonna skip the elevator problem and I'm gonna jump ahead a little bit. All right. So find this page in your notes. It's about a woman in a boat. I think it's the last page right before you get to section 4.3. Everybody got it? All right. So if you understand this idea of, velocity of p relative to a equals p relative to b plus b relative to a, this is the same thing. So it says a woman who can row a boat at 6.4 kilometers an hour in still water faces a long straight river with a width of 6.4 kilometers and a current of 3.2 kilometers an hour. Let I point directly across the river and J point directly downstream. Okay? Number 1, if she rows in a straight line to a point directly opposite her starting position, at what angle must she point the boat and how long will she take? Holy beans, what is that all about? So, here's the deal. I know what this is telling me, what this is, God, for Pete's sake, what this is telling me is that the velocity of the boat relative to the water is 6.4 kilometers an hour, right? Now, if the water's moving, that's going to change the velocity of the boat, right? But relative to the water, she can row at 6.4 kilometers an hour. Follow? So let's do this. B equals boat. W equals water, not woman. And then G, as always, will be ground.
So it wouldn't be ground?
No. Let me see if I can explain why. So she can row. Are you okay back there? Do you need me?
Yeah, I'm just done. I don't
Oh, I got you. Come on up. Yeah, you're good. Are you done now?
Yeah.
Oh, okay.
We can work on
Cool. All right. So here's the easy way to see that, Zach. So if she's in still water, she's just like in a pond, right? Rowing, 6.4 kilometers an hour, right? What if she's trying to row upstream and the stream is going downstream at 1 kilometer an hour? She's still rowing at 6 kilometers an hour relative to the water, but the water is carrying her downstream.
Oh, okay. That makes sense.
Follow you guys? It's exactly the same as walking backwards on a bus that's driving forward. Cool?
It's one of those moving ground.
Or walking across a conveyor belt. Yeah, like the ant walking across the conveyor belt. Good? Are we good? All right. Okay, so that's the velocity of the boat relative to the water. Now, the river has a width of 6.4 kilometers and a current of 3.2 kilometers an hour. So let's see. It tells us that the velocity of the water relative to the ground is 3.2 kilometers an hour, right? Notice I haven't done anything with my directions yet. Okay? These are just magnitudes at this point. All right? So, it says, let I point across the river and J be downstream. So positive J is going to be down this time, which is a little weird. Okay? So let's see if we can draw this and get a better sense for what's going on. So here's the river. Here's the velocity of the water relative to the ground. So that's going to be 3.2 kilometers an hour J, right? Now, it says that somehow she rows in a straight line across the river. In other words, she's doing something to compensate for the river carrying her downstream. Do you know what I mean? So point for me, you guys. Look. If she rows, so she points the boat straight across the river, is she going to go straight across?
No.
No, she's gonna end up down here, right?
Yeah.
So she's in this problem, she's doing something, so she does end up just going straight across the river, right? So what I know is that the velocity of the boat relative to the ground has got to be this way. Follow?
Yeah.
So let's see if we can figure out how all these things fit together. So we need to find the direction here. That's kind of our question, right? What direction does she need to row in? So,
Is that like at what angle?
yes, it's like at what angle? Exactly, yes. So, here's what we know. We know that the velocity of the boat relative to the ground is something, but what direction is it in? What direction does she move across the river when she actually moves? Straight across, right? Right? It says, if she rows in a straight line to a point directly opposite her. So she's going straight across. So this is in the I direction, right? Follow? All right, so here's what I want you guys to do. I want you to write a vector addition problem using those three terms. Don't even worry about the angles yet. All I want right now, we got to figure out what this triangle looks like. We've got three vectors that somehow two of them add up to the third one or something. We got to figure this out. So it looks to me like, I just took all the stuff off the screen. It looks to me like the velocity of the boat relative to the ground ought to equal the velocity of the boat relative to the water plus the velocity of the water relative to the ground. Do you guys agree with that? All right. So I know the velocity of the water relative to the ground. I don't know the velocity of the boat relative to the water, but I know this has to be horizontal. So I feel like my drawing needs to end up looking like this. We've got the water carrying her downstream. So here's the velocity. I don't know how to draw this. So here's the velocity of the water relative to the ground, right? Now that was being added to something. Well, it's got to be this, right? The velocity of the boat relative to the water, right?
Yep.
So that my resultant, this guy, points straight across. Velocity of the boat relative to the ground. Do you guys agree that this drawing emulates this equation?
Yep.
Right? Velocity of the boat relative to the water plus the velocity of the water relative to the ground equals the velocity of the boat relative to the ground. Follow? Are there questions? Adam, are you good? You're holding your head. Is that a, I have no idea what the hell's going on, holding of head? Or is that a, where you at?
I'll probably get it once you continue.
We have a minute.
Okay. So, now all we got to do is plug in the numbers. Velocity of the water relative to the ground was 3.2. Velocity of the boat relative to the water was 6.4. I know this is a right angle. So now you can do some trig and find this angle. And it turns out to be 30.
Will we finish the rest of this tomorrow?
Yeah, we'll finish up tomorrow. All right, so what do we got up here? Okay, guys, listen, please. All right, so tomorrow we'll have to finish the 4.2 notes. And we'll start 4.3. I still want to make worksheet 4.2 due on Thursday. All right? Try it. Like, I think you guys know enough to do everything now. I've taught you the important thing. The only thing I need to do now is another example or two. All right? Have a good day. Oh, so close.
The calculus test was easy with that method of vector cross.
Oh, good. Oh, you used that? That's the jam, right? This thing?
Yeah.
Because it's not really mathematical. It's like one of those cheesy shortcuts you can do.
Whatever.
Who do I need to email for you? Sobelak? Okay. Yeah, thank you. How was the test? Better than the first? Good. Okay. Okay. Hey, what's up? Sure, yeah.
Oh, wait.
We're good. Number 2 is at the bottom of the page. The drawing here goes to number 1. This drawing goes to number 1. There is no drawing.
Anger and what is up with you?
Hey, my guy.
We got mean and brew. I fell into the head. Shake her singing. Other word for bundle.
Okay.
I'm okay. How are you?
So if they're parallel or anti, so if they're parallel, you're going to get 7. If they're anti-parallel, you're going to get 1 or -1, right? So they're working against each other. But there's a third option. So they can be parallel, they can be anti-parallel, or they can be at some weird angle. So what's the significance of the numbers 3, 4, and 5?
Josh,
It's a right triangle,
right
right?
sectors. We don't get to choose our seats.
That's so fine. What? Over what? Like the other week.
Something quick, Brendan?
He's smart.
Okay, sorry, Dan.
It's fine. He might help
You know
out.
why I can't?
And he's
I was just
still
wondering,
guys.
was this one?
Yeah,
It's really not that bad. It's just fast paced, you know? Like there's homework every night. And then
By
there's, like,
adding,
daily
if you
worksheets
add
and
ABC
worksheets.
to both sides, this gives you
Well,
the
like,
acceleration of
it's just
AB
math. It's nothing.
plus the acceleration of
Yeah.
BC
I'll be held to the
equals the
math
acceleration
plan.
of
The way
BC.
Martin
So yes, that's the
explains
exact same
stuff
stuff.
is just
The
like.
rules work the same
Iron
for
is a shitty
position,
thing.
velocity,
Yeah.
acceleration.
Ooh,
That's part of the reason.
Follow?
Yeah.
Wait. I need you.
What?
I just have this like.
Do you mean for your answer, or do you mean to solve it?
For this problem, you know, you like. take a derivative
For the
and
answer,
look
I
at
don't
that,
care. So these
And then
ones,
she wants us to do the
like
definition.
this one here, it says, give the magnitude and direction, so you gotta do it this way.
You know what I'm saying?
Now, if the question just said, what is the displacement, then you could do it either way. And to be honest, I think in that circumstance, doing unit vectors is probably easier.
To find the left-handed right.
Does that make sense?
Right?
So, are you plugging the two into,
Yes.
putting
Two
this
plus
into
each
the
of the-
definition?
Yeah, this is the equation we're using for that.
I mean, if you were to put
Yeah, but between the paths, so that's velocity, that was, remember I talked to number 3, when we did number 3, I said, the big thing I want you to get out of number 3 is if there's a question about direction of
Oh, you
motion,
know what? No, I see what you're saying.
that depends not on the position, but on the velocity.
I should have done that.
So yeah, so here it's saying,
But we,
what's the
no,
positive direction,
I was
and
gonna
the
say-
path that it's following.
So, does that
Yeah, exactly. Does that make sense? You sure?
Yeah.
Okie dokie. And I will try to get you some more practice. I just, the problem is I'm not familiar with this book. It's got tons of good problems in it, but it's like, I need to find time to go through and,
Yeah.
1 over h,
So,
2/3, and then 1
good?
over
Out
y.
of 3.
okay.
Yeah.
Take a
No,
look at
we're
that
gonna leave
website.
the 3
If-
Okay, yeah, no, I will.
If you,
In the
And
scheme
if
of
you can
things.
send it in the remind.
I think I did, yeah. Let me know if the link doesn't work, please,
Okay.
and I'll find a better way to share it.
When you plug it, so
Cool.
you plug in 2 plus h.
All right. Oh, Arande was out today too, wasn't he?
Yeah, I don't think it was here.
Like,
I think we're still recording.
Oh, I am still recording. Oh, that's funny. Hi, Anthony. Good.